Vector equation of a plane. When we go into 3D, we can have multiple planes. In 2D, you just have one plane, which is where everything happens. But in 3D, we can have lots of planes. Think about the floor, your desktop, and the ceiling. Consider the plane which passes through the points A and R. As usual, A will be a fixed point that we know is on the plane. R would be a general point on the plane. The position vectors of these are A and R respectively, and we can see that also on the diagram. Let the plane be perpendicular to a vector n. Let R with position vector R be any point on the plane. Clearly, AR is perpendicular to N. If you think about your desk, just stand something up vertically on your desk, and then any way you place your pencil on the desk, it's going to be perpendicular to the thing that's standing up. Hence, AR.N is equal to 0. But we can see on the diagram that AR is equal to R minus A, backwards along A, forwards along R. So AR is R minus A. Replace the AR here with R minus A, and we have R minus A dot N is equal to 0. So that is R minus A dot N is equal to 0. Expanding gives us R dot N minus A dot N is equal to 0. And so R dot N is equal to A dot N. But A is a known point on the plane. N is a known vector which is perpendicular to the plane. And so when we evaluate this, it's just a number. And we often write that as small d, so we have R dot N is equal to D. We'll arrive at that over here very shortly. So expanding and rearranging gives R dot N is A dot N. In summary, the scalar product dot product equation of a plane, more often than not it's called dot product form, containing the point with position vector A and perpendicular to the vector N, is R dot N equals D, where R is the position vector of any point on the plane, N is a vector perpendicular to the plane, and D, which is equal to A dot N, is a constant as we discussed before because we know both A and N.